Hey guys, how's it going? I was going to show you how I would approach a couple homework problems. Here I am. Here I am. Hi. Hi. Should I hide myself? No, we'll see. We'll see if I freeze up again. So the first thing I do when I'm going to the homework is I go to the Canvas page. I click on this link at the bottom of the home page. I click on this big button. That brings me here if I've logged in before. If you haven't logged in before, then get on that. I have it organized by topic. You might have it organized by date. I prefer topic because it's easier for me. When I organize it by topic, if you have this, a really easy thing to do to get where you're going is to click filters, count towards grade. And now we're not doing chapter 1, so there's 0 activities, you'll notice, that updated now that I've filtered it by what the things that count towards grade for the homework. So let's look at chapter 7. Chapter 7 assignment. And you'll notice that number 1 is a pretty lame homework problem, which is why I like to show how to do it, because I don't want you wasting too much time on this unless you already have, and I'm sorry if you did. So basically, this is an old school way of taking a random sample. This is just a table of random digits. Like, they were like, hey, produce a bunch of random numbers between 0 and 9. So the very first number right here, 6. Second one was 3, 2, 7, 1. One thing that's a little confusing is they're in groups of 5. The only reason that they're in groups of 5 is to read the table more easily, because you can imagine if they were all crunched together, it'd just be like really hard to keep track of where you were at. But that's the only reason. So student government organization, pass, fail, blah, blah, blah. A list of names and addresses of 645 students. Important information right there. You guys can't even see all my pretty face. 645 students, that's important, are enrolled. Current quarter is available from the registrar's office. Using 3-digit random numbers, so we're going to pick 3 of these at a time. So the first 3-digit random number is actually 632 in the table, but we're not going to use that one. Because it says identify the first 10 students who would be selected using a simple random sample. The 3-digit random numbers begin with 816, and it tells us somewhere, okay, it says using 3-digit random numbers in row 10. That's why we're not going to use 632. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right here is the 10th row. So we want to start in that row, and we're just going to go 3-digit numbers at a time. So the first one, as they tell us, is 816. We'll watch what happens. So it should be like, oh, sweet, the first student is 816. But it's like, no, it's not. It's not. Why isn't it? Because there are only 645 students. Labeled 1, 2, 3, 4, 5, up until we get to 645. So 816 is not a student. So they found that 816 for us. They also found the second one is 283. So you kind of have to jump the gap right there to get the 3. And they tell us that. So they're kind of giving you a clue about how to use this table. Let's try that though. What happens with 283? Check it. Boom, it's golden. It works. It's green. It's green. That's good. So that one worked. 610 is the third example they give us. 610 also should work. Let's check it out. Ooh, it did work. So now we got to go. They stopped giving them to us at that point. So now you have to tediously go through the table. The next one, so 816, 283, 610. The next one is 039. 39 is another way to say 039. Let's check it out. It works. So you got to just go through and find numbers that are 3 digits, including the zeros. Notice that one started with a 0, so 039 is just 39. And then you're going to just keep going down that list, and you're going to drop any numbers that are greater than 645. Because there's 645 students. So if there's a number bigger than that, you can't use it. You just move on to the next number. So you can probably figure out the rest of that on your own. Let's check out number 7, because I want to show you how I would do this problem as opposed to how the book. Let's get rid of this. This is something else that I'm going to show you in a second, and I'm going to delete all this because I already did it, because I had to learn how to do it again. Always learning. So let's see what this says. Can we get all of this on here on the same time? We probably can. Okay, let's zoom in a little bit. Do our little calculator here. Excel is basically a sweet calculator. That's how you should think of it. The Food Marketing Institute shows that 17% of households spend more than $100 per week on groceries. Yeah, that was pre-coronavirus, right? It's like 800 now. Assume that population proportion is P equals 0.17. That's the population proportion. That's important. And a sample of 700 households will be selected from the population. Use the Z table. We're not going to use the Z table because we're going to use the sweet calculator. So the first thing it wants us to do is calculate the standard error of the sample proportion. And we know how to do that. So we're going to type standard error right here. And we're going to do equals SQRT, because we know that the standard proportion is in a square. Oh, this is backwards. That's root. Square root. 0.17, that's the population proportion, times 1 minus 0.17, close parentheses, divide it. N is 700, close it, hit it. Boom, that's the standard error. Sweet. Should we check it out? It wants 4 decimal places, 0.0142. We have to round. Oh no, I froze, sorry. I'm going to miss my movements now. It freezes up. It doesn't like it. I'm going to make this bigger now, though. Standard error. It wants 4 decimal places. Notice, rounding. 0.0142. Let's check it out. 0.0142. Check it. It's green. Okay, cool. So I usually check those because I'm pretty sure the next answers are going to depend on that. So if we didn't check it, we might just keep going down the wrong path forever, and that'd be lame. What is the probability that the sample proportion will be within plus or minus 0.02 of the population proportion? So this is one of those examples where we need a Z, I'm going to call it B. Actually, let's call it Z1. Z1 and Z2. Because I'm going above the population mean by 0.02 and below the population mean by 0.02. So I need to calculate a Z statistic for both of those numbers. That range of sample means. What's the probability we're going to land in that range? So Z1 is going to be the Z-score for, let's do the plus 0.02. Well, 0.17 plus 0.02 is 0.19. That equals 0.19, the X bar for the upper Z, minus 0.17. Notice that that's just 0.02. So we could actually have just plugged in 0.02 right here. But what this is X bar minus mu. Or actually, in this case, it's P bar minus P. Sample proportion minus population proportion. But notice, when they give you that type of a problem, that's just going to be 0.02 plus 0.02. Divided by the standard error, man. Enter. There it is. Equals. We're going to get the negative of that, right? Minus 0.02, 0.17, the population, minus 0.02, 0.15, minus 0.17. Look, that's just going to be minus 0.02. So that's our plus 0.02 z-score minus 0.02 z-score divided by standard error. Ooh, it's the negative of the same number because it's symmetric, right? We went the same distance in both directions from the population proportion. Now we need a probability, prob1, prob2. This is like us going to the z-table, except Excel is cooler than the z-table. The cool kids use Excel, not the z-table. Should we do equals? Well, that's weird looking, but whatever, it's fine. Norm, norm, dot, dist. This guy, comma, 0, comma, 1, because it's a standard normal distribution, a z distribution. Comma, true, we want it all. We want the cumulative, and you'll always do that. 92% chance of being to the left of 1.4. Less than 1.4 standard errors above the mean, above the population proportion. That's all of the area to the left, so that's not our answer. Now we want equals, norm, dot, dist. Oh. X, annoyingly, they call z x, but that's because there's a lot of different types of normal distributions. This one's the standard normal distribution. Expected value or mean is 0, standard deviation is 1, and it's true. That's the probability of being to the left of 1.41, I should have said, below. Standard error is below the population proportion. But we want between, so we can say prob between. If we double click right there, it'll open it up for us. And if we do equals, all the way to the left of the upper one, minus the stuff to the left of the lower one, that'll be the probability between, which is 0.8411, 0.8411. I'm a little scared of this one. Is it the same answer I got before? It is. Sweet. It worked. Now we got to start all over again because it says, what is the probability that the sample proportion will be, the same number. Oh, but we have a different n. And look how special this is. We just typed n right here, and then we referred to this cell. 1300. 1300 is the new sample size, n. Enter. Whoa. It all just changed automatically because I referenced that cell, right? That is sweet. So now these updated automatically because that reference worked its way through. There's a higher probability. Why is there a higher probability when we have a bigger sample size? Because that distribution is tighter. As we saw in earlier videos, that bell curve gets tighter around the population proportion when we have a bigger sample size. So let's check this out. 0.9451. Yes, it worked. All right. So there's an example of that one. That example should help you with some other ones too. So let's get out of here. Let's go to chapter 8. 8 ski. Chapter 8 assignment. What was I going to do in the chapter 8 assignment anyway? I think I was going to do 4? Yeah, like 4. The International Air Transport Association surveys business travelers to develop quality ratings for transatlantic getaway airports. The maximum possible rating is 10. Suppose a simple random sample of 50 business travelers is selected and each traveler is asked to provide a rating for the Miami International Airport. Whoa. The ratings obtained from the sample of 50 business travelers follow. Let's click on this. That's the data, but this will open it in our handy dandy calculator. I've downloaded this 3 times. I must be some kind of nerd. Let's open this bigger. Let's zoom it. We're going to make a confidence interval. The middle of that confidence interval is going to be our point estimate. X bar equals average. Click on this. Shift Control down arrow or Shift Command down arrow if you're on a Mac. Enter. Hello, 6.34 is the sample average rating. We do not know what the population average rating is. I'm going to get rid of this so it stops messing with us. Let's figure out S. We don't know the population standard deviation in this problem. So we need to use the sample standard deviation equals stdev.s for sample. Click it, Shift, Control, down arrow, or Shift, Command, down arrow if you're on a Mac like me. And let's see if they were lying about the sample size. Maybe they were. No, they weren't. That's sad. SE. What's the standard error? The standard error, if we don't know the population standard deviation, is the sample standard deviation divided by n, square root n. There it is. And now we can get our t dot 0.975. We're doing, whoa. We're doing a 95% confidence interval for a sample where we don't know the population standard deviation. When we don't know the population standard deviation, we need to use a t-statistic. What will be to the left of the upper, what area will be to the left of the upper t-statistic in a 95% confidence interval? 97.5%, because we will have 2.5% in each tail, which I went over in the last video. So if what I'm saying is confusing to you, check it out. Equals t dot inverse. This function, we feed it a probability to the left. That's why I wrote 0.975 right there. Then it wants degrees of freedom. Something you just have to remember is degrees of freedom are the sample size minus 1 for a t distribution. Close parentheses. We got to go 2.009575237 standard errors above the mean in a t distribution to get 97.5% to the left. That's how far we got to go. MOE equals, how many standard errors do I have to go? Boom. What's my standard error? Boom. CI lower, CI upper, lower is going to equal our point estimate minus our margin of error. Upper is going to equal our point estimate plus, plus our margin of error. Then that wants 2 decimals, 5.7273, 5.73. 5.73. 6.95. 6.95. It's always scary. This is the scariest part. Yay! So that's how you do Chapter 8, assignment number 4. That was pretty cool. That one was better than chapter 7, number 1, right? That one was lame. Ooh. Annual starting salaries for college graduates with degrees in business administration are generally expected to be between $30,000 and $45,000. This is why you should be majoring in economics. No, that's ridiculous. Assume that a 95% confidence interval estimate of the population mean annual starting salary is desired. What is the planning value for the population standard deviation to the nearest whole number? The planning value, something we haven't gone over, and you won't know about if you don't watch this video. Let's go to a different sheet right here. Let's zoom. The planning value is just something that some guy made up. Planning value is going to equal the maximum, 45, 1, 2, 3, minus the minimum, 3, 1, 2, 3, divided by 4. Why 4? Nobody knows. Literally nobody knows why 4. No, somebody knows, but I don't. Let's see if I even did that right. That was kind of a guess. 3750, maybe? Check it out. Ooh, it did work. That's the planning value. I wasn't lying. That's how you get the planning value. How large of a sample should be taken if the desired margin of error is as shown below, to the nearest whole number? So this is interesting. You can use some weird algebra to figure that out, or you could do our trick. Let's say sample size right here. 1. Is 1 going to be enough? Probably not. 2. Is 2 going to be enough? Probably not. But then we can just drag this. Is 2,304 going to be enough? We're going to find out. We are going to find out. What's the margin of error even going to be, dude? Margin of error? Let's do it all in one big chunk. Why do I have this? Do we need that? No. Let's move this over a little bit. So what would our margin of error be if we had a sample size of 1? So one weird thing, this planning value, when you do the planning value version, you assume that's the population standard deviation. So that's like a sigma, so we're going to use z, important, equals, how many standard errors do I have to go? Well, it depends. 95% confidence interval, so that's going to be a norm dot dist, no, norm dot inverse 0.975 is going to be the area to the left, 95% confidence interval. 0, 1, this is a z distribution. That's how many standard errors I have to go. But we have to multiply that by our particular standard error, which will be the population standard deviation divided by the square root of n. But we have a bunch of different n's, so we just click on this one right here. Oh no. Yeah, that looks right. That's probably right, so I just didn't close that parenthesis. Now we want to think, we're going to drag this formula down to figure out what this number is for a bunch of different values. But because I'm going to do that, I want to go ahead and lock this cell. I believe on a Windows machine, you can do that by hitting F4. On a Mac, I think we got to do Command T. Ooh, it worked. Or you can just literally type a $sign before each thing you want to lock. We want to lock that entire cell. So we're locking the column reference by putting a $sign in front of B. And we're locking the row reference by putting a $sign in front of 1. Enter. Nothing changed about that one because I didn't drag it yet. But then I double click it down and I'm like, whoa, So now what's happening to the margin of error as we get bigger sample sizes? Well, it's going down, which makes sense. They want to know how big of a sample size we need if we want a margin of error of 500. Well, it's either 216 or 217, right? Let's try 217 because it's less than. Let's try 217. Let's just go for it. 217. You won't be punished for plugging tons and tons of wrong answers in here, so you could just plug random numbers until it turns green. But you should get it on the first try. 200? 200. You gotta go far. Whoa, whoa. Man, working for it. 1351. 1351. Yes. How about 100? We gotta go really far. Oh no. Oh no. That wasn't even far enough. Let's highlight these and drag them down farther. No. Nope. Did we get there? Come on, catch up, Excel. Jeez, man. These guys are crazy. We gotta keep dragging. How far are we gonna go? We're at like 1 billion almost. Oh, we're getting close. Come on, do it. Oh, it's all mad. It's like getting hot. My computer is getting hot. Ooh, ooh, ooh. Whoa, I saw it. I saw the jump. 5403? That seems like a lot. 5403. Check it. Yes. Would you recommend trying to obtain the $100 margin of error? Not after all that. No. I don't know. Well, that's a subjective question, so it doesn't really make sense, but you can just try every option until it turns green. So one thing that's important to point out about this, about life, is that you could figure out these sample sizes right here using algebra, because you know the formula for the margin of error. And you could like do all the same stuff to both sides of the equation. This is what we call solving a problem numerically. In this case, you can use algebra to solve this problem, and if you like algebra, you should do that. But in life, sometimes there's problems that are ridiculously hard to solve using algebra or using calculus or using so-called math. And so often, a better solution in the world of computers is to solve a problem numerically. That is what we just did. All right? There's some cool things we could check out. We could see what happens to the margin of error. Check this out. Look how cool of a calculator this is. Oh, come on, get bigger. Oh, it did it. It's mad because we made so many. Insert, line. Notice that the bang for the buck you get on your margin of error, we like small margins of error right here. These are small, these are big. We had a really big margin of error when we had a sample size of like 1. But then as we added to our sample, it crashed, man. It got way smaller. But then notice when we added like 1 more observation when we already had thousands, the amount of value we are getting out of those additional observations when we've already got a huge sample becomes smaller and smaller. Big bang for your buck when we have small sample sizes. Small bang for your buck when you have big sample sizes. that chart shows that. You could put it in a project and impress somebody. Another thing we could check out, MOE, would be the equals confidence dot norm, because this is the other way to do margin of errors. 0.05, because the alpha is the opposite of the confidence level. The confidence level is 95%, so the alpha is 5%. The standard deviation is that planning value, comma, the size is this guy. Boom, we got the same numbers. Let's see if they keep going. No, this is what happens when you don't lock the cell. Lock it. Come on. Lock it. There we go. Now things are looking better. Let's just check a random one. Is this the same number? It is. That's another way to do it. All right. So I wanted to show you guys an example of some homework problems. I hope this helps you out. Let me know if you have any other homework questions. You have until May 22nd, 3rd, 4th-ish. We could check. Let's figure out when this is due. May 25th. Man, I was being harsh. You have until May 25th to figure this out. Hopefully this helps. I'll talk to you guys later.